Okay, welcome back. So now we have the idea about primal and dual pairs or primal dual linear programs. Now we want to give you some very interesting properties of these primal dual pair linear programs. Okay, and in total we call them duality theorems. So the way we illustrate these properties is through standard form linear programs. So the primal would be assumed to be this maximization linear form program, and the dual would certainly be this one. Okay, this is something we derived in the previous video. So if you need some derivations, you may want to go back to check that. But here we know if the primal is in this form, then the dual must be in this form. Okay. Uh, Even though the proofs that we will give you will be according to this pair, it can be shown that all the properties will apply to other primal dual pairs. It's just that we need to modify those proofs accordingly. Okay, that's something that we will not do, and we will only focus on this particular pair and the conclusion of our dual theorems. The first one is called weak duality. Is that the dual linear program provides an upper bound of the primal linear program. This is exactly how we construct the dual program, right? So this is not very surprising, but again, we just want to we just want to rigorously prove this idea. For the linear programs defined in that equation, okay, in this relationship, if x and y they are primal and dual feasible, then the objective value of x would be less than or equal to the objective value of y. So that means given any pair of primal dual feasible solution, dual provides an upper bound to the primal. Okay, that's the idea. For proof, it's very simple. X and y they are primal and dual feasible. So for C transpose X, we know it was less than or equal to Y transpose AX. Why? C transpose is less than or equal to Y transpose A. Here, if Y is dual feasible, this must be true. And also if X is dual feasible, then X would be non-negative. Combining these two, we have this inequality. And then because AX equals B, then we have the second equality. So we have weak duality. Okay, this is not very surprising because we know indeed any dual solution is will provide an upper bound to the primal. Okay, as long as it is feasible. So this is fine. So now with duality, we now can give you a sufficient condition for optimal solutions. Let me remind you something about linear programming. We have given you a necessary condition for optimal solutions. Okay, I mean a similar thing is that if there is an optimal solution, there is an extreme point optimal solution. Or if there is an optimal solution, there is a basic feasible solution that is optimal. Something like that corresponds to some necessary conditions or some properties of the optimal solutions. If I give you an optimal solution, it must satisfy whatever. Okay, that's necessary condition. Here we give you sufficient conditions. If something satisfies this condition, it will be optimal. So, if x bar and y bar, they are primal and dual feasible, that's one thing. And also their objective values are identical, then x bar and y bar would be primal and dual optimal. Okay, so I give you two conditions, feasible and the same objective value. If these are both satisfied, then the solution is optimal. Okay, proof. Given any dual feasible y, we have this, okay, by duality. X bar is nothing but one primal feasible solution. Y is a dual feasible solution, so we have this according to weak duality. But also we know y bar satisfies this, okay? Y bar transpose B is equal to C transpose X bar. So that means Y bar transpose B, okay, is this one. And this is less than or equal to any feasible Y. So that means Y bar is dual optimal, right? Because it is better than any other dual solution. So for X bar is the same thing. Okay, so now as long as you have equality here, then you have optimality. So the implication here is that given a primal feasible solution X bar, if we can find a dual solution which is feasible and having the same objective value with X bar, then X bar is optimal. Okay, a sufficient condition. With that, now let's talk about another thing. If we have solved the primal linear program, we now show that we may obtain the dual optimal solution immediately. Suppose I have this pair of LPs. If X bar is primal optimal, we know there should be a basis associated with it, right? And then we can find Y bar immediately. Y bar, according to CB transpose AB inverse, would be dual optimal. Let me say some more details here. When I give you a linear program, when I give you an optimal solution, actually no one guarantees that it is a basic feasible solution. It just guarantees that if this is optimal, then there exists an optimal basic feasible solution. Okay, so here we are implicitly assuming that this X bar is a basic feasible solution, and that's why there is a basis associated with it. But if you use the simplex method to solve the primal program, then there is no issue here. If you use simplex, then after every iteration, you get a basis. So when you stop, you have an optimal basis. According to that optimal basis, you get the optimal Y solution immediately. Okay, somewhat magic. So let's see how this is true. Because B is optimal, we know the corresponding reduced costs, which is this one, must be non-negative. Okay, this is a maximization problem. In each iteration, we look for negative reduced cost to enter, right? So if there is no negative reduced cost, this is optimal. Or if this is optimal, there cannot be any negative reduced costs. So we have this relationship. And also, we know for CB transpose, it must satisfy this equation because AB inverse times AB is just identity. So now let's examine this quantity, Y bar transpose A. Y bar is nothing but, Y bar transpose is nothing but CB transpose AB inverse. Okay, so from here to here, we just plug in this proposed solution. And then here, we divide A into AB and AN as something we are familiar with. Okay, given any basis, we divide or split the matrix A into AB and AN. The first part, CB transpose AB inverse AB, just give you CB transpose. The second part, CB transpose AB inverse AN, or CB transpose AB inverse AN. Given that B is optimal, this thing must be greater than or equal to Cn transpose. Okay, they together are C transpose. So that means Y bar transpose A is greater than or equal to C transpose. Exactly what we need to show that Y bar is feasible. And then, if Y bar is dual feasible, the last thing we need is to show that Y bar transpose B is equal to C transpose X bar. Okay, and that will tell us that these two solutions are primal and dual feasible and optimal according to proposition 3. Y bar transpose B is this one, because Y bar transpose is CB transpose AB inverse, and certainly we are familiar with this, right? This is nothing but the primal objective value. Okay, so Y bar is feasible, they have the same objective value, and then they are both optimal. So for here, If you need to remind yourself about what are them, you may want to go back to check the last video of the previous lecture. Okay, when we do matrix operations for solving simplex method, then we have these expressions. Okay, so things are very good here. Given that we have solved the primal problem, we have the dual optimal solution. And now we can prove one thing we call strong duality. For the two linear programs, x bar and y bar are primal and dual optimal, if and only if they are primal and dual feasible, and their objective values are identical. Here, we read this sentence in two perspectives. The first one is that this is an if and only if statement. If you go back to check, we gave you one sufficient condition for optimality. Okay, we mentioned that if this is true, then they are optimal. Now we are extending that sufficient condition. We are saying that that condition is sufficient and necessary. If x bar and y bar are both optimal, then they satisfy these constraints definitely. Okay, it cannot be having any exceptions. Also, strong duality strong duality makes weak duality weak, right? Because weak duality is saying the dual solution is providing an upper bound. Okay, it's providing an upper bound. And then strong duality is saying that bound is tight. Okay, that bound is tight because that bound cannot be really greater than the true objective value. That bound must be exactly the optimal objective value. Okay, so now you know what strong duality means. Let's prove it. For one direction, we have done so, right? Actually, this is not lemma 3, it's proposition 3, not a big deal. Okay, that's something we did. And now we need to prove the only if part. Suppose we have a pair of primal and dual optimal solution. Then now we know CB transpose AB inverse is a dual optimal solution, right? So the dual optimal objective value must be CB transpose AB inverse times B, and this would equal to C transpose X bar. Definitely true, okay, for this thing. And then, as Y bar is dual optimal, we know Y bar transpose B must also be C transpose X bar, right? Here the point is that I know Y bar is dual optimal, and I also know that CB transpose AB inverse is dual optimal. Because given a linear program, there may be multiple optimal solutions. We are not sure whether Y bar and the C transpose AB inverse are the same thing. But even if they are different, that's fine, because they have the same objective value. Otherwise, they cannot both be optimal, right? So we still have Y bar transpose B equals C transpose X bar. So this relationship is actually if and only if. Okay, so now strong duality certainly implies weak duality. As we mentioned, there is a bound, and the strong duality tells us that that bound is tight or cannot be improved. And given all the propositions we just proved, the primal and the dual LPs, they are equivalent, right? When I give you a primal, we define a dual uniquely, and that dual of the dual goes back to the primal. That's one thing. And also, their optimal solutions will correspond to the same objective value. And finally, when you solve one problem, you get the optimal solution of the other problem directly. Okay? So somehow solving one is the same as solving both. You have a pair of equivalent linear programs. And also, given the result of one linear program, we can predict the result of its dual. That's why they are equivalent, right? Suppose your primal can be categorized into the three situations, right? It may be infeasible, unbounded, and finitely optimal. Your dual may also be one of the three situations. In total, there should be 9 combinations, but we're showing you that only 4 of them are possible. If your primal is unbounded, okay, then that means there is no upper bound. You cannot claim that all the primal solutions are less than or equal to something, because that's impossible. Your primal is unbounded. If there's no upper bound, that must mean your dual problem is infeasible. So when your primal is unbounded, your dual must be infeasible. All the other two are impossible. If your primal is finitely optimal, then you have a finite objective value. Your dual program cannot be infeasible and cannot be unbounded, right? Your dual must also be finitely optimal. And finally, if your primal is infeasible, okay, here we know the dual may be unbounded, cannot be finitely optimal, and we can show that it's possible for both of them to be infeasible by examples. If the primal is infeasible, that somewhat means there is no lower bound for the dual. And if the dual is also infeasible, that means there's no upper bound for the primal. And that's not conflicting anything, right? So these 4 combinations are the only possible combinations. Okay, here we want to introduce one more interesting thing. Consider the dual linear program with slack variables. So here, because originally this is a greater than or equal to inequality constraints, that's minus slack variables w, and make these equality constraints. Do not forget, this is not a standard form because y are not non-negative. Here we have a very interesting proposition saying the following. For the primal defined in inequality constraints and the dual defined here, x bar and y bar w bar, they are primal and dual optimal. If and only if, okay, here what we need is a new thing. This is also a sufficient and if necessary condition for optimality. And here all we need is that w bar transpose x bar is 0. So the first thing we know is that C transpose x bar is this one, because C transpose is nothing but y bar transpose A minus w transpose. Okay, so now this can be split into 2 terms, and then the first thing here, ax equals b, so the first term becomes y bar transpose b. So we know the left hand side must be equal to the right hand side for any given primal and dual feasible solutions. Now, if the condition holds, then we know this must be the case that C transpose x bar is equal to the only thing left, y bar transpose b, and that means they are primal and dual optimal, right? Because we know they are given to be feasible, and then if they are also satisfying this equality, then they will both be optimal immediately according to strong duality. So something here is that this is a vector multiplied by another vector, and we say the result is 0. But here, because both vectors are non-negative, if this product is 0, that must be the case that each pair of variables multiplied to 0 together, okay? And that means for each primal variable, we may discuss what's happening in the dual constraint or the opposite. And here, if I have a dual constraint that is non-binding, that means this W is positive. Okay, non-binding certainly means non-binding at the optimal solution. Then the corresponding primal variable must be 0. Okay, Let me say that again. If I give you a constraint that is non-binding at the optimal solution, then at its dual program, that corresponding value must be 0 in the optimal solution. Okay, that's something we may observe in the complementary slackness theorem. And we're going to tell you why do we need that immediately in the next video. Okay, so let's do some summary. We mentioned a lot of properties of duality, right? Now it's time to ask, why do we want dual programs? Why do we want those duality theorems? If you give me a problem, I solve it, that's all. Why do I need that, right? So now I'm trying to give you some ideas. Suppose you have a linear program. We may solve it directly, or we may choose to solve the dual program and then use one of the propositions to get back to the primal optimal solution, CB transpose AB inverse, right? So that's something we may do, but this does not answer your question, right? Solving this and solving that, we are either solving one linear program. What's different? Okay, what's different here? We know that the computation time of the simplex method is roughly proportional to the cube of the number of functional constraints. Okay? And the number of variables does not matter a lot. So if your primal problem has much more constraints than variables, then solving the dual is a good idea. Because in the original case, solving the primal takes more time. But when you have more constraints than variables, solving the dual is quite possible to give you a shorter time and then the optimal solution. Okay? And certainly this is built on the fact that primal and dual problems are equivalent. If you do not have those dual theorems, if you do not know that given the primal we may solve the dual, given the dual we may solve the primal, if you do not know strong duality, do not know they are equivalent, you cannot take this advantage. There are actually many other benefits of having duality theorems. We're going to see some more in this course. So if you want to read the textbook about duality theorems and about primal dual pairs, the suggestion here is to read sections for actually 6.1, 6.4, and 6.3. Okay, these three sections contains some more examples and some more descriptions about duality. Okay, maybe from a different perspective, but reading them definitely helps. Okay, so let's stop here. Thank you.